Any study of limits in calculus cannot be considered complete without acknowledging the remarkable contributions to mathematics by Archimedes, Isaac Newton, and Leibniz. These great mathematicians changed the world of mathematics forever. Archimedes was interested in finding the areas of curves. If you look at the picture on your screen, you will understand the technique that he used. He tried fitting all regular shapes that he was familiar with into a circle to approximate the area of a circle. Eventually, with absolutely no knowledge of algebra, he came up with a pretty good approximation of pi. Isn't that amazing? Much later, Isaac Newton and Leibniz, working separately, developed the principles of calculus as we know it today. Newton was perplexed by the problem of finding the exact slopes of tangents to curves. In his study of moving objects, he encountered difficulty in finding the instantaneous velocities of objects with varying speeds. Newton's solution to this problem resulted in the birth of calculus. Most students of mathematics shudder at the sound of this word. But if you understand the basics, it is not as daunting as it might seem. The two simple geometric problems that led to the development of calculus were the investigations into the slope of a tangent to a curve at the point P and the area under the graph of a function between x is equal to a and x is equal to b. So this was the beginning problem of calculus. Let us see how we can now tackle this problem. Now look at the curve y is equal to x squared and a point P 2, 4 on the curve. In order to find the slope of the tangent at P, we draw the secant line PQ, where Q is another point on the curve. Now since we have considered Q to be a point very close to P, we can write the x coordinate of Q as x is equal to 2 plus h, where h is greater than or equal to 0 and a very small quantity. Similarly, the y coordinate of Q will now be y is equal to 2 plus h the whole squared, which we get by replacing the x in y is equal to x squared by 2 plus h. Imagine Q to be a moving point moving closer and closer to P so that PQ is becoming closer to becoming the tangent at P. Then the slope of secant PQ is also progressively getting closer to the slope of the tangent at P. As Q moves towards P, h will also become smaller so that we say h is approaching 0 and we write this as h with an arrow 0. The slope of the secant PQ can be calculated by dividing the increase in the y coordinate by the increase in the x coordinate. Now the increase in the x coordinate, delta x, is equal to the x coordinate of Q, which is 2 plus h, minus the x coordinate of P, which was 2, so that it becomes equal to h. Similarly, the increase in the y coordinate, delta y, is equal to 2 plus h the whole squared minus 2 squared, which is the x coordinate of P. This, when simplified, will become equal to 4h plus h squared. Thus, the slope of the secant line PQ becomes delta y divided by delta x, which is equal to 4h plus h squared divided by h, which when simplified further becomes 4 plus h. Now listen to what I have to say carefully. The slope of the tangent line at P is defined as the limiting value of the slope of the secant line PQ as Q slides on the parabola towards P, that is as H tends to 0. The slope of the tangent line is now given as m is equal to delta y by delta x, limit h tending to 0 of 4 plus h, and as h becomes closer and closer to 0, the slope of the tangent line becomes equal to 4. Did you get that? We know now how to find out the slope of a tangent to a curve y is equal to f squared at the point p 2, 4. But now let us find a more general equation so that we can use this equation to find out the slopes of tangents for different curves. Now look at the curve on the screen and the point P, whose x coordinate is now going to be given as P, A, and the y coordinate is f of A. Let Q be another point on the curve whose coordinates are x, y. Now to write this more simply in the form that we've just used, we can write the x coordinate of Q as x is equal to A plus h, and the y coordinate as y is equal to f of A plus h. The changes in x and y will be written as delta x is equal to A plus h minus a, which is equal to h, and delta y is equal to f of a plus h minus f of a. Thus, the slope of the tangent line to the graph of y is equal to f of x at the point P, A, f of a is given by m is equal to limit h tending to 0 of f of a plus h minus f of a divided by h. And this is the fundamental theorem of calculus. So many relationships of common interest are modeled using mathematical functions. For example, the variation of the price of fuel with time, or the change in temperature as we go higher up, or the change in velocity of an accelerating car with time. So we can see that we are always talking about the rate of change of one quantity with respect to another quantity. Normally, we represent a function as y is equal to f of x, where f of x is the function with x as the independent variable to whom we can assign values, and y is called the dependent variable because it depends upon the values of x. Now suppose that x changes from x1 to x2, then if you want to find the value of delta x, it is given by delta x is equal to x1 minus x2. The corresponding change in the y would be delta y is equal to f of x1 minus f of x2. Now let us look at the rate of change. That would now be equal to delta y divided by delta x, which is equal to f of x1 minus f of x2 divided by x1 minus x2. This is called the average rate of change of y with respect to x. The limit of this average rate of change as delta x tends to 0 is called the instantaneous rate of change of y with respect to x at the point x is equal to x1. This is the same as the slope of the tangent to the curve at the point x equals x1, as we had seen in the previous slide. Therefore, now we have the instantaneous rate of change as limit delta x tending to 0 of f of x1 minus f of x2 divided by x1 minus x2. This is also called the derivative of the function f of x, and it is represented by f dash of x. So f dash of x is the derivative of the function f of x. This is really the beginning of calculus. Now this wasn't so difficult, was it?